Hello, everyone. Okay, we are continuing our investigation of these differential equations using something called a slope field and drawing something called a solution curve, and sometimes we'll draw more than one. First, before we do that, let's go back to the discussion I gave you about this differential equation. And I said this is a familiar one. Where we've seen it before, but maybe not presented this way. And a lot of you told me, if you read the discussions, you realize that the derivative or the slope at each point equaled the y-coordinate at that point. Which function behaves that way? Well, the function y equals e to the x was the answer. Think about it. At x equals 1, if I plug x equals 1 into this function, the answer is e, right? So it's e to the first, which is e. The slope, if I took the derivative, well, the derivative is e to the x because it's its own derivative. Now, if I wanted to find the slope at x equals 1, I would plug 1 in and I'd get the same thing. So that's what I'm saying. The slope and the y-coordinate are the same. So at 1, the slope is 1. At 2, the slope is 2. At 3, the slope is 3. And it's got that exponential growth. That's why e to the x is such a cool function. You learned about it a little bit in pre-calc, but you probably didn't understand why it's so significant. It's significant because it's a function where its growth rate is equal to its output. So at every point along that curve, its output and its rate of change are the same value. It's the only function that does that. So you may not represent or recognize it in this format, but it still follows all the same properties. So for like example, if you noticed, y equals e to the x, and then you take the derivative and it equals e to the x, well, that's just y. So, I mean, it's the same representation, basically. Other things you could do, for example, you could take the second derivative of the differential equation. The derivative of y is 1, but then you took the derivative of a y term, so you need to have dy dx. And then remember, we replaced dy dx with what it is, and look, we're right back where we started. So, like I said, differential equations are just kind of a different language we have to get used to. Sometimes we'll know the actual function it represents, and sometimes we won't. So in this case, there's actually a way to solve the differential equation and find the original function is e to the x. But I'm not going to show you that today. That'll be a big thing we do next week. Today, what we are going to do is another approximation strategy called making a slope field. So we're going to make a slope field for this very basic differential equation. And then we'll do some more sophisticated examples. And I think you'll find that this is not too bad. First of all, what is a slope field? It's a visual approximation strategy. A visual way to approximate the original function. So the goal is to try to get a picture of what's happening with the original. That's a lot of calculus is all about, hey, here's the rate. What do you know about the original? So here's what you do. You have a coordinate plane typically. I'm trying to make this one not as awful as I usually do. We're only going to do it for a couple points because this gets very old very quickly. I think you'll catch on to how this works pretty quickly also. Okay. We'll also do over here. All right. So I've given a grid with a bunch of dots on it. And here's what we're saying. We have this differential equation right here that tells you the slope at each point. So this is telling you the slope at a point. So let's pick a point and I'll show you what I mean. If we started with this point, right, let's do this guy right here. So we'll start with the coordinate 1, 1. If I take this and I plug it into the derivative equation, that will give me the slope at that point. So I plug it in. There's no place to plug in x. All I do is plug in y, and I get 1. Here's what that's saying. Ready? It's saying if the original function does pass through that orange point, it has to have a slope of 1. So what we can do to show that is draw a tiny little segment. Let's make it better. Draw a tiny little segment of the curve that matches this slope. So you see how I drew a little blue curve that has a slope of 1. In other words, if the curve did go through that point, it would have that slope. Let's do another one. If I plug in the coordinate 2, 1, plug it into the differential equation, and you'd get the slope in that case to be, well, 2, again, we don't plug any x in, it's y. It's 1, so it would be a slope of 1 again. And we just keep this going for every single point indicated on the slope field. I usually will have you stop between -2 and 2. Sometimes I'll say do it in the first quadrant, sometimes the second quadrant. So you just got to pay attention because this can get, it's not hard necessarily, it just can become very tedious. So let's do an actual different spot. What about the coordinate at 1, 2? If the original function went through the coordinate 1, 2, 1, 2, this one, what would its slope be? Well, plug the coordinate into the differential equation, and you get a slope of 2, which means it would be steeper. And that's really all I need to see. I want you to show me that it's getting steeper. Same thing at this coordinate, same thing at this coordinate, this coordinate, and this coordinate. And all of those have a y coordinate of 2, and this differential equation says that the slope is equal to the y coordinate. All of these ones, if you're picking up what I'm putting down, are a slope of, oh, wait, no, that's right, slope of 1. And then what happens at like 0, for example, 0, 0. We'll plug 0, 0 in. All of these on the x-axis have a slope of, let's do better, have a slope of 0. So bam, bam, slopes of 0. Okay, so what about in the negative direction, like the coordinate 1, -1? Well, 1, -1, which is down here, if I plug that in, that's going to have a slope of -1. So it turns out that if the actual function goes through this point right here, it would have a slope of -1. Same thing with this one, same thing with this one, this one, this one. And all of these ones down here would have a slope of -2 because the y coordinate's -2. So what is this showing you? This shows you kind of a picture of little pieces of, if the function passed through this point, it's basically got to follow the motion. I almost call it like connect the dots. So what tells you how the curve actually behaves? Well, you would need to use an initial condition. So if you actually wanted to get a picture of where the original function actually is, you need to introduce the other thing called the initial condition. So let's pretend I gave you the initial condition that this thing goes through the coordinate 0 or 1, 0. No, 0, 1, sorry. Same one I gave you in the discussion. Well, it goes through this point. That means it would have to have a slope of 1 right there. And then it's almost like connect the dots. Follow along. What's going on as you move? So if I kind of pass through that point, notice what's happening. As I get up here, it's getting steeper. I don't have to go right through it, but I got to kind of follow the trend of what's going on. And it's probably going to do this. And what's happening in the other direction? Well, it's not going to go down like this because look at the x-axis. It's supposed to be horizontal. So no, you got to kind of follow the current almost. Probably something like that. You're following the current. Think of these as pushing you towards a certain direction you're supposed to go, based on what happens when you get close to it. So it's got to kind of show what's happening at each point along the curve. And this, what I just drew, it's called the solution curve through this initial condition. So what if I had given you a different initial condition? So let's say I gave you the initial condition of I want it to go through the coordinate 0, -1. Well, look what happened. Based on the slope field, it's got to look like this. And in this case, it would kind of bend this way and then come this way. So this is a different possible solution to the differential equation based on this initial condition, 0, -1. So sometimes we'll draw more than one solution curve and say, hey, look, the differential equation is showing it's probably going to have a shape that looks like this. But depending on where the initial condition is, it could be located very differently. It could be located at different spots. And we know that about derivatives. If you take the antiderivative of a derivative, remember we get a constant at the back. So that can change where the function is located. And in this case, where the differential equation is reliant on y, changing things like negatives and positives can tend to have the graph flip and do other crazy things. But that's why a slope field's cool. It allows you to kind of see what the original function is doing based on the slope at a point along the way. So let's try some other ones of these. And this is where what we're doing. So slope fields are the name of the game today. So if I give you another differential equation like dy dx equals another simple one, xy. And I want the slope field for all the same ones we just did. Let's start there. So this one will look a little more interesting than the last one because it's based on x and y, not just y. So typically I like you to do it in the from -2 to 2. Sometimes the AP test has you go to 3 or 4. They don't usually go crazy with this. So let's begin. How about 1, 1? I like starting at 1, 1 for some reason. If I plug this coordinate, so I'll show you the work one more time and then I'm going to kind of stop showing you the work because you don't need to show work for this. If I plug this point, 1, 1, into the differential equation, I get dy over dx equals, well, 1 times 1, x times y. And that's 1 for a slope of 1. Boom. I'm not going to get my protractor out and make sure it's perfect. I want it to be positive, meaning it should not be a negative slope. And don't have it be 0. Okay, 1's kind of easy. Once you get past 1 to like 2 and 3 and the steeper and steeper, it gets a little trickier. So let's try another one. How about 2, 1? Well, in this case, if I plug 2, 1 in, 2, 1 is a little bit steeper. 2 times 1 is 2. So this guy is steeper. Good enough. And then we can kind of just go for it. At 0, 1, we have a slope of 0. So basically we have a slope of 0 anytime x or y is 0. What about at 1, 2? We have a slope of 2. And look, at 2, 2, we have a really steep slope of 4. Like I said, it's hard. The AP test isn't going to go nuts on how steep you're making it. They care that you show it in the positive direction. So just try not to make it vertical, make it steep. It doesn't have to be perfect. How about down here? 1, -1, well, that's a slope of -1. 2, -1 is a slope of -2. This one's -4. This one is -2. In the other direction, right here, we have -1, 1, which is a -1 slope. Here we have -2, -4, -2. Here we have a +1 again because it's -1 times -1, +2, +2, +4. Okay, so let's sketch a solution curve through something. I'm going to do 2 of them again, 2 solution curves. So sketch the solution curve through this initial condition, f of -1 equals 1. So right here. Okay, again, start there. It's got to go through that point. And then you don't have to be perfect. You just got to follow the current. So watch, ready? This is the hardest part for students for some reason. Just start drawing and almost like, you don't have to connect the dots because sometimes you may not get perfectly to another point. But what you can do is just kind of follow the current. So definitely going this way. Now look, don't do something like that because look, it's telling you to level out. So level out, and then what? Oh, well, look what it's telling you. It's kind of telling you to bend back up. Maybe the case could be made for being horizontal, but not really, because even like at this spot, the slope should be positive. So something along these lines, and it's getting steeper. So actually, yeah, this is the case for a parabola. This is a differential equation for a parabolic type original function. Okay, let's do the solution curve from somewhere else. Let's do it between, how about at -1, -1. Oops. So through this coordinate. So look how it's a little different. It's kind of like the last one where this is negative. It kind of goes through there this way and something like that. A/B test is not going to be strict. I'm not going to be super strict. I just don't want you to break with what's happening. Clearly this one is bending down if you kind of follow the currents. If you're never quite sure, let's say you're like, man, this is tough. Plug in a halfway point. So you really could do something like a half and a half. So like, for example, if you want to know what's happening at the coordinate -1/2, -1/2, you can make this even better by plugging in a bunch of these in between spots. -1/2 and -1/2 is +1/4. So at this spot, you should have a slope of about 1/4 if it goes to that point. And yeah, you see how that kind of matches up. That's a skinnier slope than, a less steep slope than 1. So if you're struggling with slope fields and how to do it, just cheat a little bit and plug in points between. The slope field is typically not the hard part. It's the solution curve for people. They get tripped out by this. But that's why you should plug in between points if you need to. All right, let's do one more example. If you have the gist of it, that's pretty much it. So far, these two that we've done, you can actually find the original function, which I will show you next time. It's the hardest part of all this. But the one I'm about to do with you, you cannot. So check this one out. This is a differential equation. It's called not separable. Means in this class, we will never realize the original function. So all we can do are approximation strategies, the linear approximation or sketch a slope field and solution curve. So let's do that. So don't forget how to do a linear approximation. We definitely could have done that if we needed to. I'll hold off for now. Instead, let's do a slope field through just a couple of select points. 0, 0 is nice. We just get 0. Boom. 1, 1. If I plug 1, 1 into the differential equation, by the way, the notation I'm using, I'm putting it down here as a coordinate. You can do that. Would be 3 minus 2. Oh my gosh, it's 1 again. It's how convenient. And then just continue this. So if I plugged in the coordinate 1, 0, I get 3 minus 0, which is 3. Which is really steep. Bam. If I plug in the coordinate 2, 0, I get 6, which is super steep. Not a great job making it steeper, but that's fine. If I plug in the coordinate 2, 1, I get a slope of 4. If I plug in the coordinate 0, 1, I get -2. That's interesting. If I plug in the coordinate -1, 0, I get -3. That's interesting. Let's fix that a little bit. -1, 0. Yep. If I plug in this, I get even steeper. If I plug in -1, 1, I get -3 minus 2 is -5, so super steep. If I plug in 0, 2, I get -4, which is even steeper. So, and we can keep this going. Let's do one more. Let's do -2, 1. So -2, 1 would be -8, so really steep. Really steep negative. So basically then I can start to try to sketch my solution curve. And this one's a little bit wonkier. I may do one more. Let's do the coordinate at here, up here. -1 would be -3 and 2, so -7, so very steep. All right, so how is this working? It looks like if I had you sketch the solution curve through, let's say this point right here, through the coordinate solution curve through 0, 1. Well, start here. It looks like it gets steeper and steeper this direction. And then we have a pretty weird switch here, which means it's not a parabola because it's not symmetrical, but it is some kind of change from decreasing to increasing. So maybe like that, more like this. I don't know. It's not to be perfect. You can always tweak your answer as you kind of see what's going on. But that would be what the solution curve looks like. That would be one solution curve. And then you'll have to do this for different points along the way. But I think you have the gist of it. Okay, so this is another strategy for thinking about what the original function looks like given a derivative. Just now I'm giving you a derivative with an x and a y in it, so we can plug x and y into that derivative to figure out little pieces of the slope, and then we can kind of like connect the dots and find what a solution curve could look like. All right, that's it.